You know, we're surrounded by this invisible stuff all the time. Air, right? But have you ever stopped to think about what it's actually doing? It might seem like total chaos, but it turns out there's a set of really simple, elegant rules that govern this invisible world. So today, let's pull back the curtain and see what makes gases tick.
Okay, just think about a balloon. Super simple. But what is really going on in there? What are all those tiny invisible particles doing that makes the whole thing inflate, float, and yeah, sometimes pop? Answering that one simple question is actually the key to understanding an entire state of matter.
So what even is a gas? Well, at its core, it's a state where all the little molecules have basically broken free. They're not stuck together anymore, they're just zipping around with a ton of energy, they're super far apart from each other, and they have no shape of their own. They'll just expand to fill whatever you put them in. And this is where you can really see the difference. In a solid, see how the molecules are all locked into this tight, neat grid? In a liquid, they're still buddies, they're close, but they can slide around. But a gas? Man, that's just total freedom. It's complete chaos. That huge amount of empty space between the particles is what makes gases so unique. So how in the world do we make sense of all this molecular chaos? Well, luckily for us, there's a rule book. It's called the Kinetic theory of gases. And you can think of it as the official guide that describes how every, let's say, ideal gas molecule is supposed to behave. Okay, so this whole theory is built on 5 key assumptions. First, all these particles are in constant random motion, nonstop. Second, the particles themselves are so incredibly tiny that their own volume doesn't really matter. Third, they don't attract or repel each other, they just ignore each other until they collide. Fourth, when they do collide, it's perfectly elastic. It's like a game of cosmic billiards where zero energy is lost. And fifth, and this is the big one, their average energy is tied only to the temperature. Hotter means faster. Simple as that. All right, now that we know the rules of the game, let's talk about the controls. Think of these like the 4 control knobs you can turn to measure, predict, and change how a gas behaves. And it turns out they're all connected. So here they are, our 4 big factors. We've got P for pressure, that's just the force of all those tiny particles smacking into the walls of the container. We've got V for volume, that's the total space the gas is taking up. T is for temperature, which is really just a measure of how fast those particles are moving. And finally, N is the amount of gas, which we measure in moles, but don't get hung up on that. It's just a way of counting a truly massive number of molecules. And this is where it gets really cool because they're all linked. You turn up the temperature, those molecules speed up. They either push the walls out, increasing the volume, or they hit the walls harder, increasing the pressure. You add more gas, well, more particles means more collisions, which means more pressure. And if you squeeze the gas into a smaller volume, you guessed it, the pressure goes way, way up. You can't change one without affecting the other. This actually leads us perfectly into what are called the simple gas laws. A bunch of brilliant scientists realized that if you just hold a couple of these knobs steady, you can see some really clear, really simple relationships between the other two. They basically isolated these relationships one by one. First up, we've got Boyle's law. This one zooms in on that classic tug of war between the pressure of a gas and the volume it's in. The idea here is pretty intuitive, right? It's an inverse relationship. You squeeze a gas into a smaller space, you decrease its volume, the pressure goes up. Give it more room to spread out, and the pressure drops. If you've ever pushed the plunger on a sealed syringe, you felt Boyle's law in action. And the math is just beautiful. P1 V1 equals P2 V2. All that means is that the pressure times the volume you start with is going to be the same number as the pressure times the volume you end with. It's a constant, predictable trade-off. Okay, next we've got Charles's law. This time we're asking, what happens to the volume of a gas when you start messing with its temperature? Now, unlike Boyle's law, this one is a direct relationship. It's simple. You heat a gas up, it expands. You cool it down, it shrinks. This is literally how a hot air balloon works. You heat the air inside, it expands, becomes less dense, and the whole thing floats. And the relationship is just a clean, direct proportionality. As the temperature goes up, the volume goes up right along with it. Super straightforward. Okay, but what if the volume can't change? What if you've got a gas trapped in a solid, rigid can that can't expand? Well, that's where Gay-Lussac's law comes into play. So imagine you've got this sealed can. You start heating it up. Those molecules inside start moving faster and faster, slamming into the walls harder and harder. Since the walls can't move, the pressure just builds and builds and builds. This is exactly why you see those warnings on aerosol cans. Do not incinerate. This law is why. And the math shows this perfect relationship. The ratio of pressure to temperature stays constant. So if you double the absolute temperature, you are going to double the pressure. It's a perfectly predictable climb. All right, our last simple law is Avogadro's law. And this one answers what is maybe the most obvious question of all. What happens if you just add more gas? Honestly, this is the one you already know from experience. You blow more air into a balloon, what happens? It gets bigger, right? More gas molecules need more space as long as the pressure and temperature don't change. That's it. That's Avogadro's law. And just like Charles's law, it's a simple direct proportionality. The volume grows in perfect lockstep with N, the amount of gas you've got. More gas, more volume. Done. Okay, so we've got all these individual laws. Boyle's, Charles's, Gay-Lussac's, Avogadro's. They're great, but they only look at two things at a time. What if we could combine them, put them all together into one master equation that does it all? Well, we can. And that is the ideal gas law. It is the master equation. It's the one single powerful formula that takes all four of our variables, pressure, volume, temperature, and amount, and links them all together in one beautiful package. And here it is, the big one, PV equals nRT. This incredibly elegant little expression combines all of those other laws we just talked about. It's the absolute cornerstone of gas behavior. With this one equation, if you know any three of those variables, you can always solve for the fourth. It's a game changer. But here's the catch, and it's a big one. All of these laws, this master equation, they describe an ideal gas, which, doesn't actually exist in the real world. So that leaves us with a fascinating question. Out here, where things aren't perfect, when do these elegant rules start to bend? At what extremes of pressure and cold do they finally break? And why? Well, that's a story for another time.